simulation. Thank you very much.
Okay, thank you. I would like to thank the organizers for inviting me to this wonderful workshop. And I'm working on the Boltzmann neutrino transport simulation of a core-class supernovae in Japan. And my collaborators include Hiroki Nagakura and Shoichi Yamada, my former supervisor. And in this talk, I will cover this series of papers. Yeah, maybe it works. Okay. Maybe there are many talks about supernovae so far, so maybe I can skip here. But the supernovae is one of the largest explosion in the universe, and it's the most of the elements which consists of us is actually synthesized in the supernovae. And maybe also many of you may know that the neutrinos play a crucial role for core-collapse supernovae explosion. This kind of onion-shaped massive stars will form an iron core at the center, and collapse and bounce and explosion happens. So, and during the propagation of the shock wave, the neutrinos are pretty crucial to heat up the material behind the shock wave, and it is necessary to enable the explosion to succeed. So maybe I will go into the Boltzmann neutrino transport method. This is the schematic picture of the neutrinos in core-class supernovae, and the yellow arrows denotes the neutrinos, and the length, short arrows means that the mean free path is short, and the long arrows means that it's close to free streaming. So at the center, the neutrinos are most likely to be isotropic distribution, and also the energy distribution will be close to the Fermi-Dirac distribution. On the other hand, on the outside, the neutrinos are free streaming. So the intermediate region has neutrinos has non-trivial momentum space distribution. So ideally, or in a classical sense, ideally the most ideal way is to solve the classical neutron transport without considering the flavor conversion is to solve the Boltzmann equation with respect to the phase space distribution function. So this contains the spatial variable and momentum space variable. So, however, solving the Boltzmann equation is expensive. So usually the moment-based method are used for the neutron transport in the field of core-class supernovae. So we have a distribution function here, which depends on 3 variables space and 3 variables for the momentum space. And you multiply the angular cosines to this distribution function, and if you take the momentum space integration, you can obtain moments, and you can obtain moment equations. So this hierarchy of the moment equations continue infinitely, so you close this series of equations somewhere, which is typically done at the second moment. However, considering that the full momentum information is important, our group solves the Boltzmann neutrino transport simulation for investigating core-class supernovae. So there are 2 parts, the Boltzmann equation part and hydrodynamics part. So the lower part is quite common for many applications, I suppose. And the upper panel is the Boltzmann equation written in the conservative form. And this first term denotes the space-time advection, which describes the neutrino propagation in the space-time. And this second term denotes the energy advection due to the gravitational redshift or blue shift. And these orange and yellow terms are for the neutrino angular advection terms, which exists if there is, for example, if we write this equation in the general relativity, these advection terms can happen due to the light deflection effect. And the right-hand side of this equation is the collision term. So in our group, the Boltzmann radiation hydrodynamic code has been developed, and it has history since 2012, and currently it is employed with the general relativistic Boltzmann neutrino transport solver and general relativistic hydrodynamics solver. And that's enough for the Boltzmann neutrino transport simulation, and I will move on to the collective neutrino oscillation. So maybe these things are also already familiar with you, but in ordinary neutrino oscillations, the vacuum oscillation makes the flavor exchange, but in the dense neutrino environment such as quark lab supernovae, neutron self-interaction terms appear here and likely to be most dominant among the quantum kinetic equations. So, and why do we have to consider this kind of collective effect is that so far the quark class supernova simulation only consider the ordinary neutrino matter interactions, whose typical time scale will be like 10 to minus 8 or 10 to minus 7. But the time scale of the collective neutrino oscillation may be much shorter, which means that the assumption of absence of the collective neutrino oscillation and taking into account this effect is completely nonsense. So there are basically three categories of the collective neutrino oscillations, and slow and fast and collisional instabilities. And I will focus on these two in this study. And maybe as suggested, maybe the slow instability may be also important, but I only consider these two here. So the fast instability is caused by this neutrino self-interaction term, and it is caused by the angular crossing in momentum space. So since in order to judge whether the crossing exists or not, you need a multi-angle neutrino transport, unless you use AI or other methods. And the collision instability is induced by the combination of the neutrino self-interaction term and the collision terms. So collision instability is caused by the disparity in collision rates. And I will briefly talk about how the collective neutrino oscillation global simulation has been performed. The full quantum kinetic equations have been solved for the global simulation, but it is too computationally expensive compared to the classical simulation, because the typical wavelength can reach order of centimeter. So it is too fine to be employed for the compared to the classical simulations. However, there are several attempts, and for example, this paper did that in 1D, and this also. So this gives a general idea how the flavor conversion deforms the momentum space distribution, and the above black lines are the neutrino distribution before the flavor conversion, and you can clearly see that here you have the angular crossing, and after that this part is deformed as this to uh, to make the crossing vanish. So that's how the fast flavor instability is developed. Since solving the full quantum kinetic equation is too expensive, the classical simulation plus some kind of mixing is currently the feasible way. And yeah, many presenters show this figure, so maybe I don't have to explain it, but um, uh, it is still difficult to how to mix the flavors, because in general, detecting the flavor instability is a highly non-trivial problem, especially for the moment-based method. And also, even if you can detect the angular crossing or flavor instabilities, imposing the neutrino distribution after the asymptotic state of the flavor conversion is difficult when you don't have the full momentum space information. So it is still there is a lot of task remaining, but we are thinking that this is the feasible way, and we are also developing our code to include this kind of mixing. But in this talk, I will only talk about the post-process analysis. So maybe that derivation is not so important, but you have QKE, including the self-interaction term and the collision terms. And I will derive the dispersion relation and judge whether there is a growth rate, there is a mode where the off-diagonal component grows exponentially. So in order to simplify the analysis and derive the analytical formula, I further divide I further assume two kinds of things. One part is to neglect the collision terms, which reduces to the fast flavor instability. And another one is to neglect the angular distribution, which leads to the collision flavor instability. So, and in this post-process analysis, I use the analytical formula. So the growth rate of the fast flavor instability is given with this formula, where this delta G denotes the difference between the electron type neutrino and anti-electron type neutrinos. So, and as you can see here, the integrated region is plus and minus, and if this delta G takes both negative and positive values, this growth rate becomes positive, which indicates the existence of flavor instability. And yeah, basically we calculate the growth rate with this formula. And the growth rate of the collision flavor instability is performed by the earlier analytical formula, and this sigma is the growth rate, and it is given by this omega, which is given by this rather complicated formula, but this variables A, G, and alpha and gamma are given as this, where this N nu E is denote the number density of the electron type neutrinos and anti-electron type neutrinos, and the nu X and nu X bar. So, and this gamma denotes the collision rates, where you can calculate them by integrating the mean-free inverse mean-free path times the neutrino distribution function. So here's the post-process analysis. I performed the analysis for the 11.2 solar mass progenitor performed with the Latimas-Westy equation state, which is a successful explosion model. And for example, I picked up growth rate. This is radial distribution, and this red line shows the growth rate for fast flavor instability, and this blue line shows the growth rate for collisionless flavor instability. So generally, the position that fast and collisional flavor instability occur is different, but if they occur in the same place, the fast flavor instability growth rate is clearly higher. And also this color map shows how the time and radius, the growth, the instability positions are distributed. And basically, this horizontal axis means the time after bounce, and this vertical axis means the radius. And these white lines denote the different density, the radius for different densities. And this red dashed line denotes the shock wave. So the collision flavor instability is likely to be occurring in this density range, where the fast flavor instability is occurring at much larger radii. So I will go into the details of the properties of the fast flavor instability observed in this model. So I rewrite this red curve into several colors. So the different color means the different types of angular crossings. So for example, this blue line shows the so-called type 1 crossing, where the right outgoing neutrinos, the electron type neutrino is dominant. And for ingoing direction, the anti-electron type neutrino is dominant. So that's type 1 crossing, and that one called type 2 crossing is the opposite one, where the outgoing in direction, the anti-electron type neutrino is dominant, and electron type is dominant for incoming direction. And this green one denotes the crossing type, which cannot be categorized to either of them. So, for example, in this case, we observed several angular crossing points. So, and this explains the origin of the crossing. For example, this type 2 crossing was caused in between the neutrino sphere of the electron type and anti-electron type neutrinos. So, in this region, the anti-electron type neutrino decouples at inner radii. So it becomes more forward peak than the electron type neutrinos, which makes the type 2 crossing. And the outer part, the type 2 crossing, is likely to be caused by the backscattering by nucleon and nuclei. Since, as I said, the anti-electron type neutrinos decouples much inner than the electron type neutrinos, which means that it has a higher average energy, and it makes the scattering to be much stronger than that of the electron type neutrinos. So it makes the ingoing part of the anti-electron type neutrinos to be dominant over electron type neutrino. So that's the origin of the type 2 crossing occurring here. And in between, the both effects compete, so there are multiple crossing appearing. So maybe the order is not good. I will move on to the properties of CFI. So maybe you may not follow, but the growth rate of the collision of flavor instability I showed before can be expressed like this with these two limits. So I will call this upper part as the non-resonance CFI and this below part as the resonance-like CFI. And we found both of them, and I think the origin of this collision flavor instability is too complicated to explain here, but yeah, we found both type of collision flavor instability. So here's a summary of the schematic picture, and there are several important positions. And the most inner part is the part where the chemical potential becomes zero. And at here, the number densities of electron type and anti-electron type neutrinos are likely to coincide, which makes the resonance like CFI and also the fast flavor instability. And there are three kinds of neutrinosphere written like this, and the non-resonance CFI is also expected in this region, and the fast flavor instability is expected outside the neutrinosphere of the anti-electron type neutrino, like this. And I also move on to the effects of the stellar rotation, and this is the fast rotating quark-club supernova model, and this is the model with 2 radian per second. This is the model with 4 radian per second. So basically, the low electron fraction matter is extended to the equatorial direction, which makes the both collisional flavor instability and fast flavor instability to be occur near the equatorial plane. So this shows the time and radius map for the left is for collision flavor instability and right for the fast flavor instability. So basically, in the equatorial plane, the CFI and FFI are likely to be extended to larger radii, and also the fast flavor instability is occurring behind the shock wave for the equatorial plane, where for the different angle it seems almost absent. And also we investigated the equation of state dependence. We are not sure how this difference is made due to the difference of the equation states, but we also confirmed that the equation state certainly affects the occurrence of the flavor instabilities. And finally, I will explain our recent paper about the inclusion of muon. And as shown in this paper, the muons usually ignore in quark collapse supernova simulations, but they can also appear. They are thought to appear in supernova environment. So this shows where the CFI can be triggered by the existence of muon by picking up single quark supernova simulation model. So this is again post-process analysis, so it is not self-consistent muon supernova model, but this figure shows how much muon fraction is required to trigger the CFI by muon. So, and this blue and red region denotes the different tau neutrino chemical potential, and there are certainly regions where the CFI can be triggered by this small amount of muon fraction. Yeah. Yeah. So we picked up a supernova simulation model which doesn't include muon, and by assuming the muon distribution parametrically, we determine whether the CFI occurs here or not. So yeah, so basically the muon fraction here is yeah, just a parameter. Yeah. Okay. And also the growth rate can be pretty large, which is can lead to 10 to minus 2 or 10 to minus 1 inverse centimeter. If we are lucky to have the muon fraction in this range. So here's the discussion, and we are sure that the FFI and CFI commonly exist in quark supernovae, and if both of them occur in the same position, the FFI dominates. But since the CFI is likely to appear in more inner radii, which is the upstream of neutrinos, the occurrence of the CFI and that flavor conversion may likely to be affects the flavor instability occurring outside, and maybe we cannot ignore CFI for the quark supernovae. And as a future tasks, we are going to do classical simulation plus back reaction flavor conversion, such as in this paper. But since we have the full momentum space information, we can self-consistently detect the existence of flavor instability and impose the asymptotic state as we want, and that's our plan for now. So, and thank you for your attention.
Okay, can you give us, thank you for the talk, very nice. can you give us some more ideas of how you want to include this back reaction? I mean, do you want to do the Boltzmann simulation including the flavor conversions? If so, how? If not, what is the way you want to tackle the back reaction?
For example, as the maybe what's shown in Sajat's slides, that the if you have crossing like this, and if we have the crossing like this, we can simply remove this part like this, and in order to conserve the lepton number, we can just do simply increase this part or make it impose to the new x. So yeah, so there is some surrogate models suggested. So we are going to use such kind of analytical model for the asymptotic state. So does that answer to your question?
Maybe I misunderstood what you mean by back reaction. You don't mean the back reaction on the flow. You mean the back reaction on the neutrino system. What is back reaction? Back reaction of flavor conversion. Do you mean where the flavor?
Maybe the word choice was not good, but it's a contrast to our current study, which is post-process. So with this word, I want to take into account the effect of flavor conversion to the neutrino distribution and also to the hydrodynamics. That's
these are two issues. Okay. But when you want to calculate the back reaction on the hydrodynamics, you have to do it dynamically. So you have to treat it with the connection to the hydrodynamic simulation. Is it feasible with a Boltzmann solver?
Since we can detect the existence of flavor instability, and if we know how to impose the asymptotic states, we can do, I think.
What's the resolution in your Boltzmann scheme? What angular resolution do you have?
Angular resolution, it's for the it's for theta direction, it's only 10, and for the azimuth direction, it's only 6. So maybe it's not enough, but at least we have some information.
Thank you.
Thanks a lot for this very interesting talk. So actually, I had two questions. Both were asked by Thomas. So then you have, if you have 10 beams in your zenith angle, then I would assume that you will only capture very, very wide crossings.
Yes.
And mostly, very perhaps very like a big fraction of the crossings are going to be missed this way. But still, I think it's interesting to see what you observed, like in this Boltzmann calculations. Thank you.
Thank you for your comment.
Could you go back to your result about the position of CFI? Maybe your slide, your plot with position and time. Yes, that's right. So in this plot, it seems that the collisional flavor instability happens when the density is around 10 to 12 gram per cubic centimeter.
Yeah.
Right. So then, if you perform self-consistent simulation with CFI, then your result would become like 10 to 12 gram per cc model in Airing et al., right?
But that simulation assumed the flavor conversion occurs instantly, but the growth rate is not high enough to assume that it occurs instantly, so the thing is not that easy, unfortunately.
I see. I see. Understand. Thank you very much.
Following up on that, so do you, and also going back to Thomas's question, do you have thoughts on what you would do for collisional instabilities in attempting to calculate, the back reaction?
Unfortunately, I have no idea how to implement CFI. Yeah, so far. Yeah.
Okay.
If you have any good idea, please.
I don't know either.
Yeah.
What I wanted to suggest, if we want to go on a little bit discussing this, because this is the basis of the discussions that was raised, maybe those that are not necessarily right in the field that want to go and discuss and do other things, we can thank the speaker, and the people that want to stay for a longer discussion, they can. Do you agree? Okay. So let us thank the speaker again.